There are three basic ways a rig distributes or transmits power: an AC to DC power system, or SCR power system, a DC to DC power system, and a mechanical power system. At the heart of every rig power system, whether electrical or mechanical, is the prime mover. A prime mover is the rig's main source of power. Most rigs have more than one prime mover. Prime movers are almost always large internal combustion engines. Some equipment on the rig requires hydraulic power and pneumatic power. The rig's hydraulic and pneumatic systems also obtain their power from one of the three basic distribution systems. Large diesel engines are the main power source, the prime movers for most rigs. These engines often produce from 500 to over 8,000 horsepower, or 350 to 5,600 kilowatts. Rig builders usually house several engines together to drive the rig equipment. They also keep extra engine sets available for backup operations. Most rig engines are diesel because, unlike gasoline engines, they can produce a lot of power when running slow. Also, diesel fuel is not as volatile as gasoline, so it's safer to use, transport, and store. Here's an AC to DC power system. The prime mover, usually a diesel engine, supplies power to the AC generator, also called an alternator. From the AC generator, AC current is sent to the SCR, the silicon-controlled rectifier. An SCR is a high-tech solid-state electronic device. The SCR converts AC to DC current, which drives the heavy rig equipment, such as the mud pumps, the drawworks, and the rotary system. Auxiliary loads, such as small pumps and rig lighting, need lower voltage AC power, so a transformer steps down or reduces the voltage to the rig's auxiliary electric equipment. Here's a DC to DC power system. The prime movers, usually diesel engines, power DC generators. From the generator, DC current goes through a control panel directly to DC motors. The DC motors power the mud pumps, the drawworks, and the rotary system. A smaller AC generator is also part of the system. It supplies AC current for equipment that works best with this current type. For example, a chemical mixing pump requires AC power. Here's a mechanical rig system. Mechanically powered rigs are usually smaller than those rigs which use electric power. The prime mover drives a mechanical compound transmission, which in turn powers the drawworks, the rotary table, and the mud pumps. Auxiliary loads, such as small motors, are supplied with AC from an alternator connected to the prime mover. Alternating current put out by the AC generators goes through heavy-duty electric cables to a special device called a silicon-controlled rectifier, or SCR. The SCR converts AC to DC. Other heavy-duty electric cables carry DC electricity to the DC motors. The DC motors convert electrical energy back into mechanical energy to drive the powerful hoisting, rotating, and circulating equipment. Rig owners like to use AC generators because they can be built to be very powerful for their size, which is an advantage over DC generators. Also, rig equipment can distribute AC easier than DC. But direct current has certain advantages when driving large equipment. Mainly, DC motors produce a lot of torque at low speed that the drillers can easily control. Using remote switches on his console to control the SCR control panel, the driller can select and deliver the power from the various generators wherever it is required. But some AC generators power big motors. In fact, most of today's diesel electric rigs use AC generators in a system called an SCR power system. Here, a large AC generator, an alternator, is connected to the diesel engine prime mover. As the engine mechanically drives the AC generator, the generator produces alternating current, or AC electricity. AC is like the electricity used in most cities and homes. Equipment in this electrical cabinet converts, or rectifies is the electrical term, most of the AC current produced by the AC generators into direct current. As mentioned before, rig owners usually prefer DC current for driving the very large equipment that requires precise variable speed control and high torque. The control equipment includes solid-state electrical components called silicon-controlled rectifiers, or SCRs. Heavy-duty electrical cables come out of the cabinet and carry DC electricity to the powerful motors driving the circulating, hoisting, and rotating equipment. Usually, large DC motors supply power to the mud pumps, the drawworks, and the rotary table or top drive. Sometimes the drawworks mechanically drives the rotary table, but on some rigs the rotary table has its own motor. The driller can control the speed of a DC motor very accurately, which is why rig owners use DC instead of AC motors. With accurate speed control, the driller can accurately set the speed the drawworks lifts. The mud pump operates, and the rotary table turns on rigs without a top drive. Various small components on a rig need power too. For instance, these two centrifugal pumps move mud from a tank to supercharge the intake of the mud pumps. In this case, it's more efficient to use small motors to power the centrifugal pumps rather than using the prime movers, hydraulic fluid, or air. Here's another AC motor. It powers the paddles on the mud agitator in a mixing tank. AC motors generally power equipment that does not require a lot of horsepower. So they vary in power from less than 1 horsepower, or 0.75 kilowatts, to more than 150 horsepower, 100 kilowatts. For electric power distribution, some rigs use DC to DC power. DC to DC was the first electric power system. In a DC to DC system, each engine drives a DC generator. The DC generator converts the rotating mechanical energy of the diesel engine into DC electricity. Heavy-duty electrical cables carry DC electricity via the control panel to large 1,000 horsepower or 700 kilowatt DC motors. The motors convert the electricity back into mechanical energy. This mechanical energy powers the hoisting, rotating, and circulating equipment. For large equipment, most rig owners prefer DC motors over AC motors. DC motors put out high torque, twisting force at low speed. Further, the driller can easily control the torque from his console on the rig floor. Keep in mind, though, that recent technological advances are allowing computerized controls and variable speed AC motor drives to be used where only DC motors were used in the past. This is a generator, or alternator, on a DC to DC rig. It generates the AC electricity that DC to DC rigs need. The alternator powers smaller equipment on the DC to DC rig, like the small AC motors on centrifugal pumps. Air conditioners. Lights. Fans. Water maker units and other small equipment. Mechanical drive rigs normally compound or connect 2 or more engines to drive the main pumping, rotating, and hoisting equipment. Generally, small to medium-sized land rigs use mechanical drives. They use clutches, converters, chains, shafts, belts, or compounding transmissions to connect the prime movers to the driven equipment. Here's a common way to get power to the components on a mechanical drive rig. This shows 3 engines that the rig owner compounded. That is, the power from each engine goes through a series of sprockets and chains in a housing, called a compound. The compound transfers engine power to the drawworks, the rotary table, and the mud pumps. In a compound drive, engine power usually goes through torque converters to the sprockets and chains. Steel guards cover the sprockets and chains, removed here so you can see them. Torque converters smoothly transfer engine power to the compound. Here, you can see the steel guards covering the machinery in the compound. Not only do the guards protect personnel, they also keep a lubricating oil spray confined to the chains and sprockets. Also, Note that large V-belts, called power bands, drive the mud pumps. Steel shrouds also guard them. Many tools use hydraulics to transmit power. Examples include the Kelly spinner, the iron roughneck, and casing tongs. Hydraulics is a means of transmitting power by pushing on a confined liquid. Here's a piston moving inside a cylinder. Hydraulic fluid fills the cylinder to the left of the piston. The piston's surface area is 10 square inches. If a pump puts 1,000 pounds per square inch, or psi, of hydraulic fluid pressure on one side of the piston, this 1,000 psi acts on the 10 square inch piston to produce 10,000 pounds of force. That's a lot of force available for powering certain tools and equipment. Here's a typical hydraulic power pack used on many rigs. It has an electrical motor or an internal combustion engine to power the high-pressure pump. The pump takes hydraulic fluid from the reservoir and sends it out a high-strength steel-reinforced hose to the devices needing hydraulic power. The fluid returns to the reservoir after it passes through the Kelly spinner or other tool. The hydraulic power pack is a closed system. The fluid is used over and over. Certain controls, valves, and tools on the rig are air or pneumatically operated. For instance, the driller uses pneumatic controls on the driller's console to engage and disengage clutches on equipment like the drawworks. The rig crew may use air-powered hand tools, like a grinder. They also use an air hoist, an air-powered winch, to hoist and move relatively light equipment onto and around the rig floor. Many diesel engines on rigs have an air starter, which is an air-operated motor that turns the engine crankshaft over to start it. Finally, a floating rig's motion compensator operates on large amounts of compressed air to compensate for vessel heave while keeping the drill string in position. An air compression system provides air pressure to operate the pneumatic controls, valves, and tools on the rig. Rigs use rotary screw compressors or reciprocating compressors to compress air. A typical reciprocating air compressor has 2, 3, or 4 pistons moving inside cylinders. The compressor takes in air from the atmosphere and raises its pressure, that is, compresses it. The volume tank stores a given amount or volume of compressed air that is ready for use when needed. A drilling rig has many instruments and gauges. They help the driller and other crew members keep track of the drilling operation. Rig instruments vary from the most basic to sophisticated computers with video displays. Here, we'll cover the basics. The driller's console is the driller's workstation on the rig floor. It has several instruments and gauges. All of them help drillers track the drilling process and keep them informed of the situation. Indicators and gauges on the driller's console include the weight indicator, the pump rate indicator, mud pump pressure gauge, rotary tachometer, rotary torque gauge, tong torque gauge, mud return mud flow rate indicator, mud tank level indicator, and trip tank volume indicator. The weight indicator is the largest gauge on the driller's panel. It indicates the hook load and weight on the bit. The hook load is the total amount of weight hanging from the hook. Weight on the bit, or WOB, is the amount of weight put on the bit by the drill string. It is less than the hook load. The weight indicator is extremely sensitive to hook load changes. Drillers can use hook load changes to monitor the amount of drag or friction the well bore puts on the drill string when they move the pipe up or down. Or, because it is so precise, the driller can use it to monitor the operation of downhole tools requiring small variations in weight. The pump rate gauge shows the number of times one mud pump piston moves per minute. This console has two pump rate gauges because the rig has two mud pumps. The driller can determine the total volume of mud being pumped by multiplying the pump rate by the number of pistons in the pump times the amount of mud each piston pumps. The mud pump pressure gauge shows drillers the amount of pressure the pump is putting out. They monitor pump pressure from the standpipe to ensure that it is the correct amount needed to keep the hole clean and return cuttings back to the surface. The rotary tachometer shows the revolutions per minute, or RPM, of the rotary table or top drive unit. Drillers monitor rotary RPM because they need to know the rate the bit is turning. Different bits rotate at different RPMs. RPM ranges for a bit are specified by the manufacturer. Drillers use the rotary torque gauge to see how much twisting force, or torque, the rotary is applying to the drill string. Knowing rotary torque helps keep drillers from parting the drill string because of too much rotary torque. Parting the drill string in this manner is called twisting off. A tong torque gauge helps the driller and the rotary helpers make up the drill pipe and drill collars with the right amount of torque. Too little torque, or tightness in the connection, may leak or unscrew while drilling. Too much torque can damage or gall threads, which cause them to leak and eventually to come apart. Drillers use the mud return flow rate gauge as a relative indicator of how much drilling fluid is returning at the flow line. The sensor is mounted in the mud return line, the flow line. A paddle inside the return line moves as mud flows past it. As the paddle moves, it sends a signal to a readout panel mounted in the driller's control console panel. The driller sets the readout so that as long as return flow is normal with constant pump speed and output, no alarm sounds or lights up. However, when the return flow rate changes, increases or decreases, the panel's motion also changes. This change in paddle motion sends a signal to the driller's readout and sounds or illuminates an alarm. A change in the return flow rate of the mud may indicate one of two things. If the flow rate decreases, mud may be being lost to a downhole formation. If the flow rate increases, formation fluids may have entered the hole and are forcing drilling mud out. So, a mud return flow rate indicator can help drillers detect kicks and loss of circulation. This mud tank has a special float in it. It goes up or down as the mud level in the tank rises or falls. Usually several mud tanks have floats in them. The floats send a signal to a digital totalizing panel mounted on the driller's console. This panel takes the tank level signals from all the floats in the tanks, totals them, and sends the information to the chart recorder next to the panel on the rig floor close to the driller's console. If the level of mud in the tanks falls and no one has removed mud from the tanks, then it is likely that mud is being lost to a downhole formation. If the level of mud in the tanks rises and no one has added mud to the system, then it's likely that formation fluids are flowing into the well. Thus, a mud tank level indicator is another tool to help the driller detect kicks and loss of circulation. A trip tank volume indicator helps the driller monitor the amount of mud being displaced by the tubulars or wire rope being run in and pulled out of the hole. Crew members calculate tubular displacement before each trip using tables from a handbook. Then, during a trip, they compare the calculated volumes to the actual displacement. Close monitoring of the trip tank during trips is crucial to proper well control. A drilling recorder makes a record of drilling variables, such as the hook load, weight on bit, rate of penetration, torque, pump strokes, and pump pressure during drilling. It's usually located in the doghouse on the rig floor. The driller puts a chart onto the revolving drum. Several pins with ink in them trace records onto the chart. Drilling recorders may have from one to several pins, depending on how they're hooked up. The recorder gets signals from sensors mounted near the gauges that measure the drilling variables. For instance, a load cell on the deadline anchor senses hook load and weight on bit. Here's a photo of a drilling recorder. Note that it has a hinged plexiglass cover that drillers can raise to change the chart when necessary. Hydrogen sulfide, H2S, or sour gas, is the most poisonous gas encountered in drilling operations. It occurs worldwide in various concentrations associated with gas, oil, and water produced from wells. It is extremely toxic, explosive, and heavier than air. It is also colorless, so you cannot see it. In low concentrations, it smells like rotten eggs. But you cannot depend on your sense of smell to escape harm. H2S quickly deadens your ability to smell. Where H2S may be present, rigs are equipped with sensors, automatic monitors, and alarms. This is an audible and visual H2S alarm. The horn sounds a siren, while the light flashes brightly if they're activated by H2S sensors placed on the rig. This H2S sensor is placed near the mud tanks. Others may be at the bell nipple on the rig floor, shale shakers, flow line, rig accommodations air intake, and other places on the rig. When a sensor picks up H2S gas above a predetermined level, the monitor triggers both the visual and audible alarms. Upon hearing or seeing the alarm, crew members can take action to avoid injury or death. You will receive detailed H2S training if your rig is working in an area where H2S may be encountered. Distributes or transmits power. An AC to DC power system or SCR power system. A DC to DC power system. And a mechanical power system. At the heart of every rig power system, whether electrical or mechanical, is the prime mover. A prime mover is the rig's main source of power. Most rigs have more than one prime mover. Prime movers are almost always large internal combustion engines. Some equipment